This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Let's get underway for today. Today's lecture is going to be on concurrent composition. This is a very important lecture for your project design, which is obviously programming the robot Kabuki to navigate some objects. In the workshops this week, or Friday if you've already had it, but in the workshops this week for most of you, your overall task is to get the robot to navigate an obstacle. And so the simplest obstacle there is just from the top, viewed from the top, just a brick wall, which is going to be simulated by a piece of wood, basically. It's actually going to be a rectangular piece. So if you want to view it from above, it might look something like that. And the default robot behaviour, viewed from the top, is for the robot to just execute a square. Okay, I think it turns right. It doesn't matter if it turns right or left. It just executes a square. Drive forwards for a certain distance, turn 90 degrees, drive forwards, turn 90 degrees, forever. And so your goal this week in the workshops is to modify the state machine that controls the robot, that only has two states. Right? If you think about the robot's motion, it can only be going forwards or turning, or forwards or turning, or forwards or turning, into a state machine that can describe the behaviour of avoiding an obstacle. Now, in order to avoid an obstacle, you need additional sensor info. And the sensor info is provided by three sensors on the front of this that are pure signals, bump sensors. Okay, so they are just either absent or present, indicating that it's run into something. Right, so using these three sensors, you now have to design a state machine conceptually first. Right, don't get stuck into C coding before you think about conceptually in terms of bubbles and transitions how this works. The problem with trying to code something in C while you're developing it is it gets very messy. You make changes, you get confused. It's much easier to conceptually lay out the state bubbles, and then translating that to code is straightforward. Okay, as long as you get that conceptual arrangement of the FSM right. So any algorithm you can use to get around this is okay. The only requirement is that if it's initially travelling in this direction, that after it's got past the obstacle, it's still travelling in that same direction. Okay, it makes no sense to have somehow navigated this and then be going backwards or something like that. Okay, so it must be travelling in the same direction that it was initially travelling when it encountered the obstacle. So, I mean, you can play this out in terms of states. Right? You're walking forwards, you're in a forward state, you hit this, right? So it causes a reaction to your state machine. Then what do? Well, you probably should reverse or something like that. That's another state. Execute some sort of turn to get around it. Another state. Forwards, maybe the same forward state, maybe another one. And then after some distance, that can produce a reaction because you can measure the distance travelled by the robot, then perhaps execute another turn and then go forwards. So you're probably looking at maybe 5, 6, something like that, states in order just to run into something, cause a reaction in the state machine via the sensors, and then execute a series of turns, alternating turns, right, one way or one the other, and end up going the same direction around it. Okay, so the experience from those of you who had in the Friday workshop, or from what the demonstrators told me, is that a lot of people got stuck into the C coding and trying to develop the FSM of what happens in the one go, and that's where you run into problems. Okay, so please draw the bubbles about how you're going to get around this first in the workshop, or be prepared. Think about it now, and then when you get in the workshop, the coding is relatively straightforward using the template that's in there. All right. Okay, so that's your task for this week in the workshops. So, but before you actually program the Kabuki, I should say that you're going to do the simulator first. So simulate this in a virtual environment in order to make sure that it can work before you put it on the hardware. Okay, so we're going to talk today about composition of state machines. So how we can build complex state machines out of smaller blocks. Well, it implies that there's some sort of, hierarchy of design we'll see later. But if you have a state machine that controls a state machine that controls a state machine, then we need some formal way of hooking them up, so to speak, in order to have a look at the overall system behaviour from the outside. All right? And this is called, composition of state machines. So there's two types of composition. There's spatial composition. So think about that as how they're actually interconnected. We're not necessarily thinking about spatial in terms of distance. It's more about how the connections are laid out. And when I show you the structures of that, that makes sense why it's called spatial composition. And then temporal composition. So if we have multiple state machines inside, well, we want to consider it as one big state machine, when do those sub-state machines react, okay, with respect to each other? And we'll consider two cases for that. One case is simple, the other case leads down a path of many options, okay? So the whole goal of composing state machines is in order to reduce the complexity of a model. As we'll see, we'll take two state machines that will be in a cascade spatial composition, and we'll actually be able to merge them into one with a reduced space, if you like, in the sense that the FSM of the overall system is much simpler. Okay, so that's what we're doing. We want to reduce the complexity and the size of our state machines. All right, so we're going to look at, I'm just going to talk about the temporal composition part first, and then we'll look at the spatial side, but only for one of the temporal bits. It's a bit confusing, but hopefully it'll make sense in a minute. So in terms of temporal composition, we've got two things. We've got sequential or concurrent. Okay, what do we mean by this? I'll show you an example, but sequential composition in a temporal sense is what's known as a hybrid system. Now, we're not going to cover hybrid systems in this subject. If you're really super interested, it starts getting quite complex, and that's in chapter 4 of the text. So if you want to read and you're a bit curious about that. What do I mean by sequential? Well, essentially you have state machines that change their operation dependent on a mode of the system. Okay? So we call that a modal model. Now, the simplest one, which I showed earlier, is, say, for instance, trying to get a drone to do a flip. Okay, so if you think about the overall system, there's kind of 3 modes in the system where there's a different goal for each of the modes. Okay? Remember how to do the flip. We give the drone an impulse in order to imbalance it, basically, to make it flip up. Then we allow it to do the drift section where it's kind of under its own, well, it's sort of under its own power, but we don't want it to smash into the ground, right? We don't want too much power here. because remember, drones, when they're upside down, they create lift. When they're right way up, they create lift, but when they're upside down, they go down. Right? And then we need to perform the recovery, so we need to be able to then change the motor speeds and such in order to get it back upright. So there are actually 3 distinct modes here where the goal is very different. Okay, so this is what's called a hybrid system here, in that we have state machines that are essentially switched in and out depending on which mode you're in. Okay, so you can think of an FSM as a discrete dynamic system, but for the impulse it's different to the drift and the recovery modes, and you're switching between the models between those 3 different modes. So it gets quite complicated. We're not going to consider hybrid systems, all right? So that's sequential, a sequential temporal composition. Your state machines change depending on the mode you're in. We're going to look at concurrent. So concurrent is us, and if concurrent, there are asynchronous and synchronous temporal compositions. Synchronous is the easy one. Asynchronous leads us down a path where we have decisions to make about what asynchronous means with respect to sub-state machines reacting. Who reacts if the overall state machine has to react? Okay, if we're composed of multiple state machines. So we've got some interesting questions to consider. All right, so once again, our hybrid systems we're not going to be looking at, Chapter 4, if you are really interested. So in order to talk about concurrent composition, so far we've just looked at state machines that are represented by our little abstract bubbles indicating states, transitions with arrows, guards, which are logical predicates that tell us what how it transitions between states, and then actions that are specified in terms of outputs of the machine. For extended state machines, we also have variables underneath there. Okay, so remember, extended state machines allow variables to be changed. And the traffic light controller was one of those ones, where we had a counter ticking away. So here we had no, firstly remember again that with this there's no concept of time. When does it react? When do we make a transition from state 1 to state 2? Well, we know when that's enabled because the guard evaluates to true, but when does it actually do it? The timing information is missing from here because it depends, right? Depends on how this is implemented. So once again, it's important to consider there's no timing information in here. Okay, we've abstracted that out. It's just about predicting operation in terms of transition of states, not when that happens necessarily. Okay, so but we still had this little sort of diagram here. What we need to do is, if we're going to compose multiple things together, interconnect them, we need to expose the inputs and outputs of the state machines, or state machine. So we're going to use the actor model for state machines. Okay, an actor model. And an actor model, remember, has inputs, outputs, and it has some function that maps between inputs and outputs. Okay? Remember, it's a space, right? It maps functions of inputs to outputs. So this is going to be the function inside here. Okay, the actual FSM. Right, so we're pulling all the inputs out now, having them exposed, and all the outputs, having them exposed as well. We'll see what that means. It looks a little confusing. Sometimes you might think that things aren't outputs, actually. Well, they become outputs because we need to expose everything. Okay, and that will allow us to interconnect things together. One thing that will pop up often and will be confusing is what happens about timing. Once again, I'll give you an example. So for instance, if the inputs, there's a reaction on the inputs, when do the outputs change with respect to that. For these semantics here, we have no timing information about, right, how long that will take. So therefore, right, it's instantaneous. Okay, we just assume it's instantaneous. Right, so a reaction happens on the inputs, and if some guards evaluate the true and the state that you move to has a different output, this happens straight away. There is no sort of lagging of stuff going on. That's very important when we compose these things. We can't have these state machines with sort of lagging stuff going on, connecting to another one, particularly in Cascade, with a lagging thing. It gets very, very messy. We have no timing information about this anyway. Okay, so this little picture just says what it will do, but not when, okay, with respect to some time basis. All right, so we need some really formal notation. If you think about us being able to describe a composition of state machines, we have to be very careful about mapping input and output spaces and all sorts of things like that. Okay, because we're interconnecting things, it gets very important. So we're going to describe every state machine by a 5-tuple. And I don't think there's a pent-tuple, something like that. Anyway, it's a tuple that contains all of the relevant information to describe the state machine. Okay, in addition to our actual state transition diagram. What is all this? Well, remember that the actor model is mapping, it's a functional mapping. Okay? In this case, the guts of this, if you like, is the update function. Whereas in other actor models where we looked at continuous time systems and stuff like that, the integrator is like the mapping, right? Here we have the FSM as the mapping. And the update function is the real mapping, what's going on here. So let's look at this. What do we got? We got a set of states. Okay, so, you know, we've got 3 states here. So we've got a set of states that describe the state machine. We've got a set of input signals. Remember, it's a set. It could be continuous variables. It could be just absent, present, but it's a whole set and multiple inputs of differing types. Likewise, we've got a set of output. Obviously, O is for output. Output symbols. Once again, it's a space. And then U is this mapping. It's the update function mapping. And so it maps from S, right, the set of states, cross the set of inputs to, so that's the domain, to the codomain, which is a set of states, cross with the set of outputs. Kind of makes sense. And so, for instance, if we choose, say, an I, which is just some initial state, so it's a member of the set of states, and we apply the update function. So we apply a function update to some S, which is a member of the set of states, and for, this is also a problem, why did I do that? And we have C as being a member of the inputs. The mapping here maps from, you know, one element of the state to another element, S prime, and maps a particular input, call it current input, C, right, to an output. Okay, where output is a member of the space of outputs. So that's one way of thinking about this as an update function, right? It takes 2 arguments, a member of the set of states and a member of the set of inputs, and gives you a new member, the next state, of the set of states, and a member of the set of outputs. Okay. I'll also say we can, with a set of states, we also include variables in there too. If it's an extended state machine. So remember, extended state machines allow the concept of variables to be sort of persistent across all of the states. So we include variables if it's an extended state machine. They're sort of embedded in the state. If you're wondering where variables sit here, they're embedded in the state. I'll give a more concrete example. We'll look at a pedestrian controller where I'll actually tell you the size of the state space depends on the size of the variables as well as the amount of states. Okay, so that's the update function. Let's look at, we've formally defined every state machine is going to be an FSM diagram with a 5 tuple sitting there that defines the mappings, the update mapping, but also defines the input-output spaces and the state space. Okay, so there are 3 ways, at least 3 ways of doing spatial composition. If you think about how can you connect block diagrams together where you've got inputs and outputs. I'll do the first one. Side-by-side composition seems almost trivial because it's not necessarily an interconnection. I'll show you what I mean. So side-by-side, let's say you've got an FSM here with inputs and outputs. And you've got another FSM sitting here. Now, they're not interconnected in any way. But what we do is we can lump them together as part of a greater state machine, if you like, in what's called side-by-side composition. So this is, in red here, is a new state machine. It's a composition of those 2 state machines. It's like putting a boundary around it and saying, these are probably subsystems of a system. The inputs and outputs are not necessarily connected, but we're going to consider it as an overall system. Okay, drawing a box around it. That's side-by-side composition. Cascade, well, that's fairly obvious. I'm going to have to draw a cascade under here. So if we have one FSM and we have the outputs of one FSM going to the inputs of another, we can do a spatial composition around these. And this becomes a new big FSM in red. And lastly, feedback composition, for those of you who may have done control, is where we have an FSM that has inputs and outputs, and then perhaps those outputs might be also fed back in as inputs, again, to the system. And so from the outside, what we do is we just look at this. Okay, so these are 3 ways of lumping together, if you like, state machines to compose a bigger state machine. So I'm going to go through these in order. We're going to do side-by-side composition first. We'll talk about cascade, and we'll leave feedback right until last because that's the most complex one. In particular, that little thing that loops around there makes our lives difficult. Okay? And we're going to talk about that in future lectures. All right, so I will just say again that all compositions of state machines can be considered themselves state machines. Okay, so all those red boxes are state machines, right? Okay. Let's do side-by-side composition. So what we want to do is we want to take those 2 machines in white. They're represented by those 5 tuples, the set of states, the set of inputs, the set of outputs, an update mapping function, and some initial state that you start off in. Okay? And I want to compose these as some big grey box that sits around here. And once I compose that grey box, then it just looks like inputs and outputs on the left and right. And then I've got a really important question to ask. So just remember, these are those 5 tuples. I'll just point that out. Right, each has a 5 tuple describing it, with its corresponding FSM diagram. And the FSM diagram is what shows you what the update function is. Okay, so now here's an important question. When do these machines react? When do they actually react? There are two answers for this, and then there's multiple answers within one of the answers. So how these reactions of composed machines is coordinated is what's going to be called a MOC, a method of computation. And we'll explore that in a bit more detail. So I think the best way of describing this is on the next slide. There are two ways of describing how these machines react. So either they react together at the same time, and we call that in lockstep, or we call that synchronous composition. Synchronous concurrent, right? It's getting a bit tricky here, right? A synchronous concurrent composition, or they do it independently, which is an asynchronous concurrent composition. Okay, so I think this is best shown by a very simple example. We'll take two independent FSMs. Remember, look, these FSMs don't share inputs and outputs, okay? And we're going to compose them in two different ways, and I'll show you that the overall composition of their FSM diagram is very different, depending on if you allow these to react, they have to react at the same time to their inputs, or they're allowed to react independently of each other. Okay, what I mean, but they are independent in terms of the inputs outputs, so I mean independently in time. Okay, they can react at different time points. So let's look at a really interesting example. Let's take two trivial state machines, really simple two-state state machines, and they are clearly independent. They actually have no inputs, right? It's just two outputs, right? State machine A has an output A, state machine B has an output B. Okay, just to get rid of any confusion, the states are labelled differently between the two things, but they're independent. One other thing I'd have to also point out that's the default state for the state machine B. So I want to compose these into an overall state machine that represents the behaviour of both of these things in the one go. Now, if you think of this, the space of states here, it's just S1, S2, right? It's a set, it's only two in the set, and the set representing all states here is just S3, S4, just option of two. You got one or the other, and that's all you got. Okay? Now, the composition, the set of states of the composition can be equal to the cross of all of the set of states of A and the set of states of B, but it also can be a subset of that as well, as we'll see. Okay, it might be smaller. The space is smaller than just the cross of both of them. Okay, let's have a look. Let's do synchronous composition first. This is synchronous composition. So here in C, over here, this is my composed state machine. Synchronous. Both machines react at the same time. Okay, even though right, they don't even have any inputs, right? And they're not dependent on each other as such. This is the composition of the machine here. Oh, sorry. That was pretty dumb. I forgot. That's the composed model. So what do we do here? We now combine new states to represent the state of both of the subcomponents. Okay? So what happens here is that both of these machines react simultaneously. That's what I should have drawn here. So think about it this way. Okay? They both start off in initial state S1 and S3. And these guards are true, so they'll always be taken. When will they be taken? We don't know. But we just know that they'll be taken at the same time. Okay, true, they're always going to be taken, but we just don't know when. So that means that while this transitions to S2, this simultaneously transitions to S4. Okay? And we can represent that in a diagram here which shows that the initial state of the composed model is S1, S3, right? They both start here. And then at some particular time, they both transition to, well, A goes to S2 and B goes to S4. So we represent that as this combined bubble here, showing the combined state of the system. And we also translate the outputs across, so you can see when this transitions to S2, the output is absent for this machine, but when this goes from 3 to 4, the output is B. So in this case, the output's it's B. And once we're here, and that guard's always true, so when we do take that transition, that we then migrate back to the S1, S3 joint state. Okay, it's fairly obvious, like it makes sense, doesn't it? So the output of this machine, you could consider, it's a machine that alternates between A, B, A, B, A, B, right? It's clearly alternating between those two outputs because it's either going that transition or that transition, A, B, A, B, A, B. But the composition, the composition of states S1, S4 and S2, S3 are not reachable, okay? We could never get the case where you end up in S1, S4 because if they both default to this state, then on the next reaction, they will both migrate to S2, S4, right? You can never get it being in S1, S4. So there's no entry to this state, right? From either of these states here, there's no entry to it. And in particular, obviously, if you were in S1, S4, which I don't know how you could be in, but if then you had a reaction, you would end up in S2, S3. Right? So we can explicitly show that if you were in that state, maybe there was a hardware failure or something funny, and it ended up here, that you could actually be in this loop forever, right, going between these two states here. So excusing failure, right, that this machine will output AB, 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 AB forever, and these are unreachable states. So you can prove that, formally prove that those states should never be, all things working, never be reachable, okay? Right. So that's the easy one, the synchronous machine. What about an asynchronous composition? Ooh. So, of these two machines, now all guards are true. But asynchronously means that they can change at different times. So A could transition earlier than B, or B could transition earlier than A. Ooh. It starts getting very messy. This is the resultant composed model of the system now. I'm going to explain a little bit about what this interleaving semantics business means in a minute. But if we now basically allow them to not transition at the same time, we get more possibilities, okay? So for instance, if state machine A transitions before B, then obviously we'll end up in a state where an S2, S3 joint state, right? This one has transitioned before this one has. Okay, so we have that possibility now. And consequently, the other way, if B reacts before A, we can actually end up in a joint S1, S4 state here. What that means is that all the states are now reachable. You can see all those four possible combinations of states are reachable because you're allowing for things to happen out of order. Now, interleaving semantics, what does that mean? We are only allowing one or the other reaction to occur, but not to occur at the same time. That's what interleaving semantics means, okay? So in other words, we're not going to get a transition from S1 to S3, S1, S3 to S2, S4, okay? So there is no direct transition this way. Okay, so interleaving means It's one or the other. It has to be A or B or A, right? It cannot be both at the same time. That's okay, we can allow that. So they're not allowed to simultaneously react. And you notice now that we have non-deterministic transitions. Okay? Depending on which one is reacted, right? So it's non-deterministic now. Right? Some other external mechanism might decide which one reacts, or the environment might decide which one reacts. Okay, so in the side-by-side composition here, when you are composing two models like this in side-by-side composition, you've got some important questions to ask. Are you going to compose them synchronously or asynchronously? Now, synchronously means obviously we know that both will transition at the same time, so we will have only a reduced possibility of the amount of states that we could end up in. If asynchronous, do we allow simultaneous transitions in A and B? Do we always assume A reacts before B? Do we interleave it? Do we flip a coin? Right? What's the mechanism for choosing which one reacts first? It's probably environmental that may determine that. So therefore, we have a non-deterministic system, right? What determines which, from here, what determines if it takes that path or that path? Well, some external mechanism will do that. Okay, we just show that both possibilities are allowed. And so how do we choose whether A or B reacts? Well, the answer is different. As I said, it depends on the assumptions, it depends on the environment, it depends on the system. I'll show you an example of this later on. Okay, so that's side-by-side composition. What about cascade composition? This is probably the more important one in terms of thinking about blocks of connecting things. So we have a 5-tuple representing state machine A, 5-tuple representing state machine B, and we want to represent the entire system as a grey box with a 5-tuple around it, representing it. Now, it's very important in our semantics of how we're describing this that there is no concept of flow of signal, if you like. Okay? So you may think that A always has to react before B. Right? Well, because the outputs of A are the inputs of B, and depending on what state you're in and depending on what your inputs are, tell you which is via the update function, tell you what state to be in next, which tells you what the output should be. Okay? It's very important though. We are not, that depends on time, right? There's time taken for things to happen here. We're not worried about that. Okay? As we'll see when we do a composition. Right? So there's no concept of A reacting necessarily before B or having to react before B. Okay? They're happening concurrent. For the concurrent composition, it doesn't matter what order they react in, basically. Okay, we'll see that in a minute. So I want to take you back to, let's go back to this first. We looked at a time-triggered stoplight intersection. And it was a very simple one. It's not allowing multiple traffic flow. It's just basically, this represents the lights for one direction, it shouldn't matter actually, 2 directions of a car at a pedestrian crossing. So it's very simple. There's one set of lights. You don't need to worry about crossroads or anything like that. And we had this little state machine here that was an extended state machine because we had counters running that kept track of time. Okay? And if you remember, we started off in a red state. After the count gets above 60, then the guard becomes true. We turn the green signal on. We end up in the green state. If a pedestrian comes along and they push the button, if it's been in the green state for longer than 60, basically it will go straight to yellow. Otherwise, it goes to a pending state where it still gives the traffic time to cross, and then we'll go to yellow. Okay? So this counter here is serving a couple of purposes. Note again that there's no concept of time. This is not necessarily, this count is not seconds, okay? This is just a count. What dictates the count? So for instance, when is this transition taken? Well, it depends on what the rate of the counting is, okay? Which is, once again, not important for this, right? Now, we're going to actually tie into this a little pedestrian light. So think of the pedestrian light as being the crossroads, if you like. And clearly, from the obvious design perspective, if you're a pedestrian and you've got two lights, red and green, right? You want to push a button, for instance, and then when it's green, you want to be hoping that the cars are red, okay, and vice versa. When you are red, then the cars are probably green, okay? So we can describe the pedestrian light behaviour very simply. And we're going to assume, it has to start in some default state, we're going to assume it's in the green state so you can walk, right? And when we come into this default state, the pedestrian counter has its own extended state machine, it has its own counter variable. It's going to start at 0 and it's going to tick at some rate. Let's be pedantic about it. Let's call it 55 reactions. What is a reaction? It could be one reaction a second. It could be one reaction a minute. Depends on the underlying timing. Okay, it stays green for 55, right? We just keep updating this internal variable p count. When p count is above 55 or greater, that guard is satisfied, and therefore we go to the red state. And as soon as that guard is satisfied, PED-R is present. Okay, it's a pure signal, so it's going to actually fire the real light, right? Control the real light. When we're in the red state, we can only get out of the red state if sig-R is true, that guard. Okay, it's present. So what does that mean? That's coming from the traffic light. So that's telling you that the traffic has been stopped. Okay, so if then, we can go to green, right? And we set the pedestrian green light to be on. We reset the counter and then we update the count again. So the light's going to stay green for 55 seconds, basically, for the pedestrians to cross. Okay, reactions, I should say. We'll assume it might be seconds. Let's compose the two models together. So it's a cascade composition. We have up the top our traffic light controller with the 3 light outputs. We're tapping into the R light, the red light, and we're running our pedestrian light controller off that. And here, we've got the 2 outputs to the pedestrian lights. Making logical sense. One question is, if we draw a big red box around this and have it as a composed state machine, what's the size of the state space of the composite machine? Now you might look at this and say, well, this is a 4-state state machine, and this is a 2-state state machine, so therefore the composition must be, at the maximum, must be 8 states, and maybe smaller. But there's one very subtle thing hiding inside here. For extended state machines, when you have variables, they technically expand the state out. What do you mean? Well, let's say we're in the green state here, right? And count is actually increasing, right? Right, on every reaction of something, it's causing count to increase. That actually effectively multiplies the state space out in a subtle way, right? So this is not really a sort of, it's 4 states, but inside the states, the variables are adding much more multiplicity to the states. Kind of makes sense, right? State means you've got to remember where you are. So you remember not only what state you're in, but also the variable counter you're up to. So it's kind of buried in the state, state of spaces. Okay, so the size of the state space of the composite machine, it's not 8, it's big, right? Because we've got 61 possible values for count in each of these states, and we've got 56 possible values for p count in 2 states. So the multiplicity, it's big. The dimensionality is big of this. Okay, let's look at what the composed FSM looks like. So we have to go through and enumerate all the possibilities here. This is the asynchronous cascade composition, okay? So we are going to assume here that these things can only change at the same time. All right, so they're synchronous, in lockstep with each other. And if you think about the interconnection here, maybe there's some sort of common clock that's going to both of these things that is only allowing transitions at the same time. So this is what happens, right? So we get all the possibilities. We start off in the default state of red for cars, green for pedestrian, right, as we see from the individual state machines. And therefore now we have to enumerate all the possibilities from there. So for instance, we could imagine, well, the only way to get out of this state is for it to go to the, so for P count, so we want to transition green, the pedestrian green to red, right? So what happens is green to red. And that doesn't cause a transition on a reaction, on the traffic side of things. It becomes red, red until the count, its count hits 60. Now, it so happens that when you're in this default state, you reset both the counters. They're both adding to 1. When P count gets above 55, we go to here, and count is still increasing. When it gets above 60, we go to the opposite, green, red. In other words, it's like a 5-second overlap where both lights are red. It's a bit of a protection mechanism, right? Stop red light runners and all that sort of thing. So there's 5 reaction overlap here, and we migrate to then the green-red case. These are just the compositions of, once again, looking at the corresponding reactions on both of these diagrams here. What's interesting to note is when we enumerate and draw in all the possible reactions, that there are a bunch of states up here that are unsafe. Okay, so they've sort of been linked up here. In other words, green, green. That's highly unsafe, right? Allowing cars and pedestrians to go. We could consider yellow and green to be unsafe as well, right? We don't want cars going through on a yellow and pedestrians still walking. And the same here, pending and green. So pending was this temporary state, if you like, where we were still waiting for a counter to tick to give cars enough time to cross. So there would be cars crossing at the same time as pedestrians. So these are technically unsafe states. But notice when we enumerate all of this, there's actually no way of getting in any of these 3 states. We start in this default. The only transition out of it is this one, and then you're in this sort of sub-loop here, or possible loops around here, and return to here. There's actually no way of getting in any of these 3 states. So we can safely say that this machine, well, we can actually formally prove that it's safe, that these 3 states can never be entered unless something bad goes wrong. Okay? And if you did end up in these states, we could then still predict the behaviour about what will happen. And you can see that eventually it's probably going to fall back to this state here, and saving another failure, we'll end up in the safe area of things. So we can actually remove those unreachable states. Once again, this is assuming a perfect world. We can say, yes, we can formally remove those because they can't be got to in any way. And so this is the cascaded composition of the 2 machines. Right? So this now represents the entire system. So we've simplified it effectively. I'll give you a very, very brief example of a more complicated system. I won't talk about it too much because it's a bit more complicated, and I want you to think about it. If I describe it, you can think about it in your own time. So let's look at a system where this might be a web server. Let's think of a web server where maybe you might have multiple sub-machines that can handle requests. Okay? So each machine would have its own state machine, physical machine. Let's keep it really simple. Physical machines that a request comes in and it's routed to both of the machines. Okay? And the machines can be in two states, an idle state or a state where it's actually serving the request. Now, what happens here is that these machines share a common variable called pending that can keep both machines, even though they look independent, both can tell if there's still tasks that need to be served, okay? And they can also increment or decrement that variable, okay, depending on if a request has come in. So we actually end up with so we can choose if we model this as a synchronous or asynchronous composition here. It turns out for machines like this, an asynchronous composition is a smart way to do it. Why? Because in the serving state, we don't know, basically we don't know how long it's going to take to serve the particular request. The requests could be very different requests. So we allow the machines to react asynchronously, right? It makes no sense to have to wait, for instance, for this one to make a transition in order for this one to make a transition, okay? Now, all of these non-deterministic loops here might look crazy, but what I want you to do is I want you to look at the conditions here and realise that there's some external mechanism that's going to choose which one of those transitions that occur. Sure, these guards here, right, can evaluations about which one you follow, but you can have multiple one of these ones evaluate at the same time. For instance, request and request. So this one will output done, this one will request, this one will just increase pending by 1. Okay? So this is a very interesting side-by-side composition, but there's still a link where there's a variable that's shared between the two things to keep track of this, what's pending to be served, and both can increment and decrement it. So I want you to have a look about it and just follow it, try and follow it through from the perspective of jumping between states of these two things here. As I said, it's a bit too much to ramble on about in a lecture. Now, I'm going to quickly talk about feedback composition. We're going to focus a bit more about this later, but feedback composition is quite difficult. Why is it difficult? It's difficult because the same argument here, right? So in order to determine via the update function what your next state is, you need to know your input, but your input is part of your output. So we need the output A2 before we can determine to know what the input A2 is in order to use the update function to then map to the next state. So the composition machine of this is very tricky, and we may have to take into account timing or other detail in order to actually be able to realistically model this. It's very subtle, this little connection here, right? It turns out you can actually translate any composition of state machines into a feedback composition. Feedback composition is very hard to understand, but if you understand it, you understand all the other compositions easily, okay, because it's the most general way of doing it. All right, we'll leave it here for today. Next lecture, we're going to talk about hierarchical state machines. So it's where there's a state machine within a state machine. So it's not composing ones, it's a sub-state machine inside a state machine. It's going to get fun. All right, we'll leave it there.